Hello everyone, thank you for coming back on April the 16th. So this is our second last Thursday of the class. We will have a lecture today, lecture Tuesday, and then lecture Thursday, and then nothing until the exam. So I just wanted to, before we started going over the content for today's class, I just wanted to show everyone where we have this content for the lecture today. So we're not really in particular module content anymore. So last lecture, which was kind of an exam review lecture, and the next three lectures, including this one, which are sort of in preparation for the final, I've put here on my courses under final. If you go into practice exams, down here, this is the link for the lecture we had last class. And I'll drop the lecture from this class and all the next classes in this same place. So you can find that, again, if you go into content under the final in the practice exams. So before we get started, I did just want to say thank you to everyone who has filled out their course evaluation. As I said, I do think that this is an important resource for us, especially this year. So I really appreciate people taking the time. We've got just over a quarter of the class who have done this. So thank you very much. I appreciate your feedback. Again, there's also a means for anonymous feedback through the My Courses website if you're interested in leaving feedback there as well. So this is the calendar that we put up last week. Right, so today we're on the April the 16th, and we will review the practice exam 1 that's on the course. So this is before, maybe 3 years ago or so, there used to be midterms in heat as well as case studies, so people would have to do both, and these are solutions from the midterms from each of the modules. So the module we're going to go through today is the first module, which is kind of general heat transfer knowledge. So we'll start with the multiple choice questions. The structure of these practice exams are 10 multiple choice questions and 2 long answer problems. So these are, particularly I think for the multiple choice, these are the types of multiple choice questions that you might see on a final. So this first one says, which of the following order of terms correctly matches the following descriptions? So here they give us 3 descriptions. The first is energy transfer due to random molecular motion and bulk fluid motion. Energy transfer by photons emitted from matter due to changes in electron configuration. And energy transfer from more energetic to less energetic particles in matter due to particle interactions. So here I look at letter I, and that's because it's talking about random molecular motion and bulk fluid motion, that's convection. So I know right away I can eliminate option A, option C, and option D because they don't start with convection. Now the second one, energy transfer by photons emitted from matter due to changes in electron configuration. Maybe I don't feel super confident in what this one is, but the next one is energy transfer from more energetic to less energetic particles in matter due to particle interactions. So this is talking about diffusion of heat in a solid. So we have, or at least it's in a medium. And I know that radiation doesn't need a medium because the sun can radiate heat to us through space where there's nothing, right? So I know that the third one is not radiation, which means the second one must be radiation, and the third one is conduction. So here my answer is B. The next one is kind of a conceptual question, but kind of a math question too. It asks us which of the following equals the total thermal resistance from the temperature A to the temperature B in the thermal circuit below. So here we have 2 networks, so 2 resistors in parallel, And then those two resistor parallel networks are chained together in series. So if I was just doing resistance 1 and 2, so what's sort of an effective resistance for 1 and 2, if I put them together, I would add them up like resistors in parallel, like I see here. And I would do the same for 3 and 4. But then since these two resistor networks are both in series, I would then add up these resistors. So here, the answer is A, and the math is shown here. I won't try to verbally give you what the math is. So this is sort of how I would try to do it, is reduce each of these different components. Multiple choice question number 3 asks us, which of the following best describes volumetric heat capacity? So is it the ability of a material to transport thermal energy? That sounds a little bit more like maybe conductivity. The rate at which thermal energy is transferred per unit area. So I know that heat capacity, right, is sort of talking about how much energy we need to increase a temperature, right? So this is talking about a rate, so that's probably not the right one. The ability of a material to store thermal energy. So one way that a material stores thermal energy is by changing temperature. So that one's looking promising. D is the ratio comparing the rate at which heat transfer occurs with a fin and without a fin. So that's talking about fin effectiveness. And E is the ratio comparing the ability of a material to transport and store thermal energy. So that sounds like some kind of a dimensionless parameter. So here, the answer is, I'm not clicked on the right thing, is part C, the ability of a material to store thermal energy. 4 asks us, which of the following expressions is Newton's law of cooling? This is kind of one of these engineering decoder ring type questions. This is definitional. So we use Newton's law of cooling to describe convection heat transfer. So that's this option C, which gives us an equation for heat flux due to convection. Question 5 asks us, what is the rate of heat loss from a 10 centimeter diameter ball that is 100 degrees Celsius when it's located in a large room with air and wall temperatures of 25 degrees Celsius? The convection coefficient is 10 watts per meter squared Kelvin, and the emissivity of the ball is 0.4. And they tell us how to calculate the surface area of a sphere. So here, because they're telling us about the convection coefficient and the emissivity, and they tell us the air temperature and the wall temperature. So there's a couple hints in this problem that are pointing us towards remembering that we have to deal with convection from the ball, but also radiation. So the total heat loss from the ball is a sum of the heat lost from convection and the heat lost from radiation. I can calculate the heat loss from convection as H times A times delta T, where my delta T is the surface temperature minus the temperature of the fluid, in this case air, far away from my ball. And I can calculate heat lost from radiation using the emissivity, Stefan-Boltzmann's constant, area, and the T surface to the power of 4, or T of the ball surface to the power of 4, minus T of the surrounding surface to the power of 4. So in here is the assumption that we have a small object, my ball, in a large enclosure, which is the room. To do both of these things, I need to calculate the area, but the problem tells me how to calculate the area of a sphere, just in case I forgot. And I can get a value for that, and I'm told all the other properties in my equations, so I can see that the heat transfer from convection is 23.6 watts, which is an answer here. So if I forgot radiation, I would have picked E, but I remembered that radiation is in this problem as well. But I also have to remember that anytime I'm talking about a temperature that's raised to a particular exponent, I can't use Celsius. I would get a very different answer if I took 0 to the power of 4 and if I took 273 to the power of 4. So I have to use absolute temperatures when I'm using the equations for radiation. And if I remember to do that, and I can look up Stefan Boltzmann's constant, then I have radiation heat loss and convection heat loss. I add those two things together, and I get 31.8 watts, which is pretty close to 31.7 watts. So maybe there's some kind of rounding issue here, but it's clear that the best answer for me here in question 5 is D. Question 6 asks me which of the following assumptions are true when I'm applying the thermal resistance method. So thermal resistances are great. They're a very powerful tool, but hopefully one of the big things we're learning in this class is we can't just apply a solution method to a problem. We have to know that it's admissible, right? We need to know what the assumptions we're making are. So this is asking what assumptions do we have to make if we're using thermal resistance. So I'm just going to go through these individually. So I know I can use thermal resistances. This first one says 1D conduction, a metallic solid, and heat generation. So I know that I can use thermal resistances for more than just metallic solids. So I'm going to cross that one out. I also know one of the things we did when we went from Module 1 to Module 2 was we were then able to start dealing with temperature distributions inside materials that were generating heat. I can't use resistors for materials that are generating heat. So that eliminates a couple options here as well. I also know in all of my equations for resistance, I have properties, right? Maybe it's the conductivity of a solid, or maybe it's a heat transfer coefficient. But if those things are changing with space or with time, then I can't really use those resistance equations. I would have to use some kind of differential equation to solve my problem. So I know it can't be variable properties. So at this point, the only answer, and we know that we can, so here in D, we know that we can use, here it says negligible radiation. So I don't have to neglect radiation to use thermal resistances. We have an equation for resistance when we're using radiation. So I'd already eliminated D, but I guess I can eliminate it twice, right? So our only answer here where all of our options are available is option C. So we're going to pick that one. Question 7 asks us which of the following scenarios allows us to define radiation heat transfer as heat transfer equals emissivity times Stefan Boltzmann's constant times area times Ts to the 4 minus T surface to the 4. And then it tells us what Ts and T surface are. So here my options are only when a medium exists between an object and its surroundings. I know this is not true because I don't need a medium for radiation heat transfer, so it's not A. When the object surface is gray in color and the surroundings are black in color. So we do use the terms when we're talking about radiation as like a gray body or a black body, but this doesn't refer to the material's actual color. So it's not B. Option C says only when the surface absorptivity is larger than the surface emissivity. We're not exactly necessarily sure about that. Maybe you're, so we can leave that one. It ends up not being true. In this case, we're sort of assuming that these two things are equal or approximately equal. When you have a small object that's a gray surface in a large enclosure, which is a black body. So this might, your spidey sense might start tingling here because this equation is the equation that we use. There's two, right? There's one equation for small object, large enclosure, but we had another equation for parallel surfaces. So D looks pretty good. E, whenever your professors say so, this is not a good way to go through life. You'd like to be able to make your own decisions and not just do whatever your professors say. So we're going to say that the answer here is D. Question 8. Consider a heat sink that has 64 round pin fins, we're given some geometry, with fin efficiencies of 0.8 and a convective coefficient of 20 watts per meter squared Kelvin. Assuming the exposed base surface area is negligible compared to the fin surface area, what is the heat transfer rate across the fin system if the base of the fins is maintained at 90 degrees and T infinity, or the ambient air, is 25 degrees? So this is a math question. We're going to have to get our calculators out. We need to know how to calculate heat transfer from an array of fins. So here we're going to use this equation. From a single fin, we would get rid of the capital N, which is just the number of fins. So here we have the number of fins multiplied by the fin efficiency, which we're given, multiplied by the heat transfer coefficient, which we're given, multiplied by the area of a single fin, so we can calculate that, multiplied by the temperature difference, T at the base minus T infinity. Remember, that's kind of what the efficiency is telling us. Is it's kind of, if the efficiency was 100%, then we would assume that the whole fin is the same temperature as the base, right? And as the efficiency drops, it just means that the temperature is not uniform on the fin. So here I just have to calculate the area of the fin. So this is going to be the surface area. So I know all this information here, right? So I'm just plugging numbers in. But my surface area here is going to be the perimeter of my fin, which is pi d, multiplied by the length of my fin. Because the area I want is the heat transfer area. So in this case, I guess I'm neglecting the area on the tips of the fin. So here I got 10.45 watts. Now I know that this is an approximation, that there could be also a little bit of area on the tips of the fins. So if it was 10.5 watts, right, so it'd be a little bit higher. So 10.5 seems reasonable. If there was another answer here that was maybe like 11 watts or something, I would maybe go back and look at this area calculation and add the tip area of the fins. But here, because the next highest number is 17.3, and I don't think my area is going to go up by 70% by adding the fin area. So I just used the more simple calculation. But it would be more correct to calculate the total area of the fin. But it's an exam, so I wanted to do it a little quicker. Question 9. I think this is a good one conceptually. So it says, for this figure to the right that's shown up here, which of the following sets of statements is correct if the system's at steady state? Right? And then it tells us something about what's going on with the heat that gets transferred at each one of these boundaries. And what about the heat flux? So it's really important that this problem tells us that it's at steady state. Because if it's at steady state, then that means the temperature, so our system is not storing or losing any energy. So that means if it's at steady state and nothing is generating heat, then all the energy that's coming into each one of these surfaces is equal to all the energy that's leaving each one of these surfaces, right? And this heat transfer is constant at each one of these boundaries. So the amount of heat that's transferred through each of these boundaries is the same. So I know it's got to be C, D, or E. Now, the next part, right? So it asks us about the heat. So I know the heat's got to be equal. But then it asks us about the heat flux. So now here, I know that the picture here is maybe not great. But as we get these concentric circles, right? So as the radius gets bigger, the area gets bigger too. So there's the smallest amount of area at Q1, and there's the largest amount of area at Q3. So I remember here that the heat flux is Q divided by A. So if all the Q's are the same, then the one with the smallest area, right? So A1, Q flux at 1 is going to be larger than the heat flux at 2, which is going to be larger than the heat flux at 3. So in this case, the correct answer is E, where all my heat transfers are equal, but my heat fluxes are increasing, or are increasing as I move towards the center of the circle. The last question is asking us about how do we use shape factors. So we have this material that we're seeing here. We wanted to determine the power consumption of a proprietary low-power disk-shaped computer processor mounted on a circuit board using heat transfer concepts. The processor diameter is 3 millimeters, and the thermal conductivity is given. From thermocouple measurements, so basically we measured some temperature. The processor maintains a uniform temperature at 50 degrees Celsius, while the temperature of the circuit board surrounding the processor is 33 degrees Celsius. What is the power consumption of the computer processor? Assume all the heat generated by the processor transfers to the circuit board and there is negligible contact resistance. And then they tell us the shape factor. So here we're trying to find the heat that comes out of this disk. So for shape factors, we take S times the thermal conductivity of the material multiplied by the temperature difference. So we know S is 2D, so twice the diameter. I put that in. I know all this information now. I put it into my calculator, and I get that the heat is 5 watts. So those are the 10 multiple choice questions. Do we have any questions or comments about the multiple choice part of this exam? Okay, then we'll move on to the long answer problems. So the first long answer problem looks like this. We're supposed to consider a 20 meter long insulated pipe. It's located in a room with air and wall temperatures of 25 degrees Celsius. And we have the dimension and property of the pipe and insulation are defined in the figure. We know that pressurized steam is running through the center of our pipe at 140 degrees. And we give an internal convection coefficient, so the convection coefficient here at the center of our pipe. And then we're also given an H value at the external part of our pipe. And we're told, at least initially, to neglect radiation. Part A asks us to determine the heat loss from the pipe. Just let me close my email here, just in case we get another. Sorry about this. Right? So we're asked to, I'm going to cancel that. We're asked to determine the total heat loss from the steam pipe, and then we need the surface temperatures to be below 60 degrees. So we're asked what the surface temperature of the pipe is. And then for part C, we're asked if the outer surface of the insulation has an emissivity of 0.1, show quantitatively, so do some math, and show that the radiation isn't important for this problem. So the first thing I always like to do on these long answer problems is draw the problem out better. So again, I'm a big advocate of bringing like colored pencils to your exam. I think for me, it just helps me conceptualize things better, right? You obviously don't have to do that. So my system looks like this. This is the information that I know. And the first thing I'm asked is to find the heat loss from the pipe. So I'm going to assume that the system is at steady state, that material properties are constant, that we have 1D conduction outward. So the pipe is kind of long enough that the only way we're transferring heat is out the sort of radially out from the center of the pipe to the outside, that there's no heat generation, and that radiation is negligible. Right? The problem told me to assume that, and we'll check that sort of at the end. We're also told that T infinity is equal to T surroundings, and I think we were given a value for that, maybe something like 23 degrees or something. So if I try to make a little bit of a cross-section of what the system looks like here. So we know that at the center of our pipe here, we have hot steam at 140 degrees Celsius. Now, I could draw sort of a first law analysis, maybe a control surface at any one of these different surfaces and find that the heat going into that surface would be equal to the heat coming out of that surface. Right? And then I'd want to chain up the resistances so they go from the one temperature I know to the other temperature that I know. Right? So here we have resistors in series. So we start at the hot steam. Then we have resistance to convection from the steam to the inside wall of the pipe. Then we have conduction through the pipe, so we need a resistance for that. Conduction through the insulation, so we have another resistance. And then another resistance on the outside of the pipe from that outside surface to T infinity. And then I know T cold on the outside. So I like this because I have a resistance network that goes between two temperatures that I know. So if I knew the total resistance, then I could find the total heat transfer. Because I know that for any resistance network, 1 over the total resistance multiplied by the temperature difference across the resistance network will give me my heat transfer. And this would be great if I knew the total resistance, but I don't. So, I have to work this out analytically, right? So I have 4 different resistors in my network. 2 of them are convective resistances, and 2 of them are conductive resistances through a cylindrical surface. So I look on my equation sheet and I can find resistance for convection, which is 1 over HA times the length. And then I have this equation here with the natural log on top for my resistance to conduction through a cylindrical shell. So it's nice. I've got these equations, and I feel like from the picture of the problem, I know all of this information. So I'm going to start to calculate things. I know that I can get my total resistance here if I could find the resistance of each of these components. So I'll start with my first convective resistance. I know HI, I know R1, and I know L. I got to be careful with my units here because I think that they tell us the lengths maybe in terms of centimeters or millimeters. I always want to convert to meters instead of centimeters or meters. I want watts instead of kilowatts. I want joules instead of kilojoules. I always want to be in the base unit type, and then I'll worry about conversions at the end. So in this case, we have a relatively small resistance. My resistance is in degree Kelvin per watt, which is good. That's the unit that I want. So, I guess I've said this throughout the course, like, I can't prove that I'm wrong, which is not quite as good as being right, but it's certainly better than proving that I'm wrong, right? So here now I can do the same thing for my conductive resistance through the first part. So this is through the pipe and not the insulation, right? So I got to make sure that I'm pulling the right values here, that I'm taking the conductivity for the pipe and not the conductivity for the insulation, that I'm taking. So this natural log term is always the larger of the 2 radii divided by the smaller of the 2 radii. So it's R2 over R1. So I should get a positive value in the argument for the natural log. I put a number in here. Here the resistance is super low. So it's like 2 orders of magnitude. So it's like 100 times less than the last resistance. So I probably don't even need to worry about this resistance in my calculation, because if I'm adding them up, it doesn't really add anything. Which it kind of makes sense, right? So the pipe has kind of a thin wall, and it's made of metal, which is conductive, so there's not a lot of resistance. The whole purpose of the insulation is to add resistance, so I'm kind of expecting this to be a fairly large value, right? It's the same form as the last equation, but I got to make sure that I pick the right radii, and I pick the right thermal conductivity constant. So I put that in. And here, now you see these other terms were all, times 10 to the negative something. And this, I guess, is as well, but it's times 10 to the negative 2. So it's at least an order of magnitude bigger than all of the other terms that I've calculated so far. So this, to me, at least conceptually, is starting to make sense that my resistance of the insulation is bigger than the other resistances, which is good because that's its purpose. And then I can find the resistance to convection on the outside of the pipe, right? So now I got to make sure I'm picking the right heat transfer coefficient and the right radius. And I put this in. This is reasonably large too. So I'm going to use all of these resistances because I've calculated them all. But I would probably get the same answer if I just added up these two for the total resistance. Because these ones are sort of rounding errors, especially this one that's times 10 to the negative 5. Right? So if I add all these things together, I calculated all these terms, so I put them into my calculator, right? And I get that the total resistance is 0.047 degree Kelvin per watt. But the problem doesn't ask me for the total resistance, it asks me for the heat transfer. So I can put that into this equation now, right? And I'm carrying my units, right? So I have 1 over this total resistance, right? So now my degree Kelvins are in the denominator of this equation, and watts are going to flip up to the top, which is nice because I want my heat transfer in watts. And then I'm multiplying by a temperature difference in Celsius, but, you know, because the lines are the same distance apart, if my thermometer is in Celsius and Kelvin, it ends up being the same because it's a temperature difference. So those Kelvins are going to cancel out. I'm going to get something in watts. And in this case, I get 2,465 watts. Or if you wanted to put 2.46 kilowatts, that would be okay too. But here, because I just put everything in meters and watts and joules if I had them, then I'm just going to get an answer here in watts. So that's good. I know the heat transfer. The next thing I want to do, I want to make sure that this pipe is safe so that if, you know, a worker in my plant touches it, they don't burn themselves, right? So here we have this resistor, and I know that the heat is the same through every part of the resistor, right? So the resistance will change, but I want to find out what my temperature is after the first 3 resistors. Right? So I can do this 2 different ways, right? So in purple, I'm looking at, I can find the temperature difference between TH and TS using my total heat transfer. And in orange, I can just use this resistor over here, right? Because the heat's the same. So the total resistance for the purple part of the circuit is the sum of the first 3 resistors. The total resistance for the orange part of the circuit is just the 1 resistor. So I'm going to calculate, you wouldn't do this on a test. Well, I guess you could if you had enough time. I'm going to calculate this both ways and show you that the answer is the same. So here I can isolate, if I just take the purple part and I know that it equals Q total, then I can multiply up by the sum of those 3 resistors and isolate for TS, which is the surface temperature, that's what I want. And I get this equation. I put in the information that I have into my calculator, and I find that the surface temperature is 54.6 degrees. And I think the problem said that the regulation, sort of the standard here, is that you want it to be less than 60 to avoid people burning themselves. I think it's kind of like if you touch something that's less than 60, or that's 60 degrees, it's something like you can touch it for 5 seconds before you get burned. So your brain has enough time to be like, oh, that's hot, I'm going to take my hand away. Right? We see, I got a 2-year-old in the house, so a lot of times you see these real-time calculations be like, I'm touching this thing, and it's hot. Maybe I should not touch it. And then she lifts her hand away, but sometimes it's too late. Right? So here, right, so we can do it the purple way here, right? But if I wanted to conserve sort of keystrokes in my calculator, I could do it the orange way too, just go between TS and TC, and I should get the same answer. So I'm just going to show you that that's the case. So here, now I'm only dealing with 1 resistor. I'm going between TS and TC. So now this equation looks close to the same, right? TC, this is my cold. So you can get this analytically, right, if you sort of do this. But you can also just see that I know TS has to be bigger than, this is the coldest temperature in the problem out here. So I know the surface temperature has to be bigger than the temperature in the atmosphere. So I know here that I got to take TC plus something positive to get a number bigger than 25 degrees. So I put this information in my calculator and I get the same answer. So this is the kind of thing where if you did have extra time on an exam, this is one way you could check your work. But I wouldn't, unless you were finished everything, I wouldn't calculate this both ways. This is also kind of, I guess, an argument for writing things down symbolically and solving each particular term. Because you could have got to the end of the first part, if you just put it all into your calculator, you wouldn't know these individual resistors. And you'd have to calculate them again, which, I don't know, maybe that's better, maybe that's worse. But there's some process, I think, to efficiency on an exam. So you just have to, I mean, you've written enough exams. So the next part says, show that the radiation isn't important if emissivity is 0.1. So there's a couple ways to do this, and I'm going to do this in a way that's different, that's on the written solutions that are posted on the website. So the way that I think about this is if I can find the resistance, we have this resistance network, right? If I can find the resistance from this radiation and compare that to the total resistance, then I can see if it matters, right? Because if the resistance is really low, or the change in the total resistance is really low, then I'm going to get the same answer, right? So here, this is just a slide from the review lecture, but I have a way to find resistance from radiation. So to do that, I take 1 over this radiation heat transfer coefficient multiplied by the area. And my radiation heat transfer coefficient is a little bit ugly, right? And again, I got to remember when I'm doing this that because I have some temperatures to the power 2 here, I want to use Kelvin, right? So if radiation was important, then my circuit would look like this. It would be the same all the way up to the surface of the pipe, but then I would have these two resistors in parallel. So I don't even need to see what the impact on the total resistance of the problem is. I can just see what's the resistance if I take these two parallel resistors, and does adding the resistance from radiation change anything? So I'm calling this resistance at the end. So that's this kind of two resistors in parallel, right? I have an equation for that. And now I already know the convective resistance here, but I want to find the resistance from radiation too, right? So here I have this equation for H rad times A, right? It's kind of a beast here. So, you have to put this all into your calculator, right? But we do that, we have to use our temperatures in Kelvin, right? Otherwise we'll get the wrong answer. So I put this into my calculator and I find that 1 over HA, or I find that H rad times A is 2.83 watts per Kelvin. So now my resistance at the end is going to look like this. And I might at first start to look at this and say like, oh, 2.83 is a lot bigger than 0.012. So maybe radiation is going to be important. But it's important to remember that here we're going to add up the reciprocals. So we'll see what happens when we do that. When we take 1 over 0.012, we get 83. And when we take 1 divided by 0.283, we get 0.35, right? So when I add those two things together, I get something that still looks very close to 83.3, right? Now it's 83.7. It's almost the same. And if I invert that, then I get that the resistance of these two resistors in parallel is 0.0119, where before it was 0.012. Now here, because these are basically the same number, I know that the effect of this radiation is not that important. So I think that's how I would show that resistance to radiation is not that important, that I get basically the same answer if I included the radiation or not. Now again, I mean, maybe you're in an application where that extra 1% difference matters, right? So that's, as an engineer, you have to understand your application. But I would think in most applications, this is probably fine, especially if you're doing analytical calculations. So that's the end of problem 1. Does anyone have questions about how we approached this problem? Okay, we'll move on to the next one. You'll notice a theme in these problems. So, I don't know. I don't think I'm outing him here, but Professor Charlot, who also sometimes teaches heat, is kind of an enormous Star Wars fan. So all of his questions are about Star Wars. In this case, we have the Millennium Falcon, and it's our job to evaluate the performance of an 8 kilowatt electric water heating system for the hyperdrive. We know it's going to fail because the hyperdrive on the Millennium Falcon always fails, right? Water's at 20 degrees, and it flows into the water heater at a rate of 4 liters per minute. Again, my spidey sense is tingling when I see that 4 liters per minute because that unit isn't a good unit. I don't want to deal with that, so I'm going to convert that into a mass flow rate, and my time unit is going to be in seconds. If the water heater surface temperature is 45 degrees Celsius on the entire surface, and it's subjected to surrounding air at 23 degrees Celsius with a particular convection coefficient, what is the temperature of the water leaving the water heater? We're also given an emissivity of the water heater, right, which sort of tells us radiation might be important, and we're told the surface area of the water heater as well. We're also given some properties of water. And it's nice they gave us the conversion in case you haven't on purpose or inadvertently memorized it. There are 1,000 liters in a cubic meter. Right, so here we're going to assume that the system is at steady state, that all the material properties are constant. We're going to assume this every time, so at least write this down on all of your long answer problems, that the materials or properties are constant, that we have an isothermal outer surface. We're told that was measured. And we're going to assume that radiation can be modeled as small object in a large enclosure. So we can use that equation. That's why we're making that assumption, so we can use that equation that we use. We're going to assume that the convection coefficient is also uniform over the whole surface, and that the T infinity is equal to T surroundings. Oh, we got one more. I guess, so here we got water that's flowing through the through our device here. Now, we're going to assume that it just changes temperature, that it doesn't boil. So if this was heat transfer class and it boiled, then you'd have to start dealing with, how do I calculate the enthalpy? What's the pressure? What's the quality of the water as it leaves? But here we're just going to say that it just goes from cold water to hot water. It's always liquid. And then the change in enthalpy can be approximated as Cp times delta T. So this is what my hyperdrive component looks like. I know coming in, I've got some information about this cold water. It comes in at 20 degrees. It comes in at 4 liters per minute. So I'm going to turn that into a volumetric flow rate that's in meters. So now this is in meters cubed per second. So I had to divide by 1,000 to get to meters cubed. And then I had to multiply by I had to divide by 60 seconds per minute to get that. And I'm told what the CP is. I think they told me the density was 1,000. So then I just multiply that by 1,000 and I get the answer. If they don't tell you the density of water, just use 1,000 because it's always about 1,000 if it's liquid water. I don't know the temperature at the outlet. That's what I'm trying to find. But I know that this thing generates 8 kilowatts of heat, right? So that's what we're trying to do. We're trying to get rid of that heat, right? I'm also told the surface temperature on the outside of my component, its emissivity and its area. And then I'm told far away from the device, I have this ambient temperature and also the temperature of a surrounding material, right? And here I also wrote, again, the emissivity and the area. So from the outer surface of my material, I know that I'm going to be convecting heat, to that T infinity. And I'm also going to be communicating with the surroundings by radiation. So there's going to be radiation heat loss and convective heat loss. So I know exactly what you're thinking when you look at this picture is, I really should do a first law analysis on this problem, because that's what we do in heat transfer, right? So if you're ever in doubt, that's at least the first option, is like, what would the problem look like if I did conservation of energy on this problem, right? So here we do a control volume around our whole open system. Because it's an open system, I'm going to use this version of the first law, where my energy stored is equal to the energy coming in minus the energy going out. That's energy not by mass, right? Plus the energy generated, plus this energy that's coming in and going out with the mass, which is accounted for here. So in this case, my problem is at steady state. There's no energy coming into my system, so there's no sort of solar radiation or anything coming into my problem here. I do have energy going out, and there's two components of energy going out. I want to make sure that I don't mess up my sign, so I'm going to put these in brackets, but I could also make this negative Q convection minus Q radiation. I do have an energy generated term, and I know that I've got m dot Cp times delta T here because I've got water flowing through my system. So this is going to be my equation, but the value that I want to know is the cold water temperature out. So here I can isolate for T cold out, right? And I get T cold in plus this. Now, here, you just got to trust the first law with the signs here, because this negative component is staying negative over here. So I might get a little nervous about this, right? So here, because I know that my cold outlet temperature, because it's taking heat away, I'm expecting the cold outlet to be higher than the cold inlet, which means that I think the energy generation term must be bigger than the heat loss by convection plus the heat loss by radiation, because I'm expecting this term here to be positive, right? So I think that I shouldn't have 8 kilowatts of heat lost by convection and radiation. It should be something less than that. So here I know TC in, I don't know Q convection, I don't know Q radiation, I do know the energy generated, and I know m dot times Cp, right? I'm trying to find TC out. So this is not too bad. I know maybe half of the things that I need to know, and hopefully I can find equations for those other things. So first, I'm going to look for the convective heat transfer from the surface of this component to the atmosphere. So this is going to be H times A times delta T, where delta T, so the way this equation was set up is that we want it to be a positive number. So it's going to be a positive number, and I let the first law deal with the signs. So here, to get a positive number, I multiply by the surface temperature, which I'm assuming is higher than the temperature at infinity. So Ts minus T infinity. I know these values, and I put them in, and I get that Q convection is 880 watts. So that's good, because I know that, or at least I feel like Q convection plus Q radiation shouldn't be bigger than 8 kilowatts. So this is good. I'm not even at 1 kilowatt here yet. So that's good. Now, the one of the two things I didn't know, I know now. So that's good. Right? So now I'm going to try to find the radiation heat transfer. Right? So here I'm making the assumption, we wrote down in our assumptions list, that we were going to say that this is a small body in a large enclosure. And we do that so that we can use this equation. Right? Again, in the first law, I want this to be positive. So Ts should be bigger than T surroundings. So I've set up my equation like this. I remind myself that because I have T to the 4 here, I don't want to mess up my units. So I use absolute values of temperature here. I put this information in my calculator, and I get that this is just under 145 watts. So that's good. Now I know everything in my equation. So I can write this out here. I know that I come in at 20 degrees inlet. I can add up these loss terms, and the sum of these things is still negative, but it's less than 8 kilowatts, right? And I know m dot times Cp is down there. The one thing that I do have to do, because I'm going to show you carrying the unit, so I didn't turn this 8 kilowatts into 8,000 watts right away. But I carry, it's okay. It didn't burn me because I'm carrying my units through my calculation. So here I multiply this 8 kilowatt term by this multiple, knowing that there are 1,000 watts per kilowatt. Here I put the watts on top because I want to be left with watts and I want to get rid of kilowatts. So kilowatts has to be in my denominator here. And that 8 becomes 8,000. So when I do that, I get this term, which I can simplify. Again, I like to, even I did this as an undergraduate too, I would write out each of these terms. It takes me a little more time to write it out, but if I mess up, I don't have to go right back to the beginning. And I see that my temperature of the cold fluid at the outlet is just under 45 degrees Celsius. And that's what the problem asked me for. So at this point, I have finished that first exam. So does anyone have questions about this second long answer problem? All right, well, that's the end of the exam review, but if anybody has questions kind of about the course, what we intend to do moving forward, I'm happy to field those questions now. Is the assumptions will count points? Yeah, so typically we ask you to include assumptions because it's part of the grading scheme. So I think that's one of the really core parts of this class is that you need to be able to understand why you can use the methods of analysis that you're using. And writing down your assumptions is really a key part of that. So definitely assumptions will be graded on the exam. Second question, how many long answer questions are there on the exam? So on the final exam, we will have 20 multiple choice questions and 3 long answer questions. Yep, 20.
Are you still planning on separating the multiple choice and long answer?
Yeah, that's our intention, or at least that's my intention. I have a meeting with Dr. Du today at 1 o'clock, so we're going to sort of discuss exam logistics. So, yeah, my intention is for those 20 multiple choice questions to be given through the My Courses website as a quiz, and we'll make that available for some amount of time. But that time won't coincide with the SIS time, if I have my way. And then the time that with the 2.5 hour block, the nominal 2.5 hour block, and obviously you'd get whatever extended time you've been approved for by the university. So that 2.5 hour block, we would give you to do the 3 long answer problems. But obviously that time would also include you accessing the exam, and then you sort of cam scanning it in and submitting it. We did talk about some sort of submission method where maybe by the end of that 2.5 hour period, maybe you've submitted your answers again in a quiz and sort of like just like your final answers for each part. And then maybe there's some short grace period after that time where you would be able to upload your solutions, and then we can grade them just in the same way that you grade your homework. So I guess the other part that I'm interested in, I know the department, we've been asking for conflicts for a little while, and I know some people have responded, but if you do have a conflict with an exam, or if you're in, I think we're a little bit lucky that our exam is at 4:30, but if you're in a time zone that you feel is different enough that it may cause, some difficulties accessing the exam, let me know, and we'll do our best to find sort of a suitable way to administer the exam to everyone. Any other questions? All right. Thank you very much, everyone. Appreciate your time. I hope everybody stays safe and that everybody's doing well, you and your families. And I will talk to you again on Tuesday, if not before. I do still have office hours too. So if you intend to use my office hours, please send me an email and I'll make sure that I'll be there. Thank you very much.